All right, next up, what we have is what we call the electromagnetic spectrum. So you can think about this as different colors of light. However, what we see as visible light as colors is only a small part of this spectrum. So let's just say that light is a small part of the electromagnetic, which is called EM spectrum. Right, so visible light only makes up a small part of it. The rest is invisible to the human eye. That doesn't mean that it's not there. It just means that we don't have the right equipment to see it, right? So here I've got this little cool diagram with what is electromagnetic spectrum. You can see the sources right down there on the bottom left and bottom right. But anyways, what you can see here is that this little part of the spectrum, that's visible light. The rest of it is invisible to our human eye. So we've got all kinds of cool things. Over here, we've got radio waves, right? What makes your radio work, microwaves for microwaves, infrared, that's used on some TV remotes, not necessarily all of them. It's also what allows us to use night vision goggles, so that's pretty cool. After that becomes the visible light, then the ultraviolet or the UV, so that's what gives you sunburns. The X-rays, right? That's how you get X-rays, and then gamma rays, right? Generally don't want to be near any of them. So let's take a look at how this all works. So the energy and color of light is determined by the wavelength. And we'll get to that in a second, right? So in terms of visible light, think about back to art class, we've got Roy G. Biv. So that's the colors: red, orange, yellow, green, blue, indigo, and violet. On the R side, we have red light, and that's generally low energy light. And then on the opposite side, we've got violet, which is high energy light. The way I like to memorize that violet is the high energy light is because of UV light or ultraviolet light. And that's what causes sunburns and skin cancer. Right, so that's ultraviolet, and that's obviously high energy because it's causing the damage, and thus it's right next to violet, which means that violet is higher energy than red, right? And you can see that in this above diagram, right? If you take a look at the purple over here, the violet, right? This high energy is on the right, low energy is on the left. So let's talk about what wavelength is. So if we picture a wave, might look something like this. Right, and then just kind of split it somewhere down the middle. The wavelength is the length from peak to peak or trough to trough. And wavelength gets a special symbol, and it's this Greek letter lambda, right? So that's lambda. And so if we take a look at this light and then compare it to another wave of light, maybe something that looks like this. Right, then something like this to this would be the wavelength of this light. And so what we can see is that in the second light, we have a shorter wavelength than the first light. And when it comes to the energy of the light or the color of the light, it depends on the wavelength. And the rule is that the shorter the wavelength, the higher the energy, right? So I'm going to write smaller wavelength equals higher energy, right? And you can think about it, more peaks are going to hit you at any one time. And that's what this diagram shows as well, right? On this high energy gamma ray, X-ray, right? You see very short wavelengths. On this lower energy, you see a very long wavelength, right? Radio waves not going to hurt you. And that's the same thing with color. So something like purple has a shorter wavelength than something like red, which is a lower energy type of light. So one way to think about it is the wavelength. Another one is frequency, which gets the Greek symbol nu. And frequency is just defined as the number of crests, so the top of the wavelengths that pass through a point in 1 second. And so it's basically how many, if these waves are moving, how many peaks are you going to hit per second? And so if you think about it, it's going to be inversely proportional to the wavelength. So this short wavelengths, you're going to get a lot of peaks hitting you in 1 second. These long wavelengths are longer, so you're going to get less of them to hit you per second. And so here's the relationship. If we have a low wavelength, we have a high frequency, and thus we have a high energy. And then the opposite, right? A long wavelength will be a low frequency and will equal to low energy light. So the wavelength determines the color or the type of light, right? Whether it's going to be red, orange, blue, gamma rays, X-rays, radio waves, that kind of thing. But there's another factor of light that you might want to consider, and that's the brightness of light. And how do we represent that as a wave? So that's where the amplitude of the wave comes in. So let's take a look at this. Just going to draw a sample wave section there, and then I'm going to try to draw a wave with the same wavelength, but just lower amplitude, right? So if we take a look at these two waves, they have the same wavelength, or at least approximately, right? I've tried to draw it so that they have the same wavelength. And so since they have the same wavelength, they're the same color or type of light, right? So they're both either red light, or they're both blue light, both radio waves, right? Whatever that wavelength is. And then in terms of that brightness of that light, how bright that is, that's determined by this height of the peak, right? Or what we call the amplitude. So you can see in this top picture, the amplitude is much larger, and so that becomes a brighter light. Right, larger amplitude equals a brighter light. And so that was a principal question in physics and chemistry, is what is light? And after a couple experiments, they kind of determined, okay, light is not a thing, it's a wave. But the weirdness of the quantum realm continued, and actually Einstein figured out that light also has particle properties under certain conditions. So sometimes light acts like a wave, sometimes it acts as a particle, but for the purposes of our course, we're mostly going to consider it a wave. We'll talk about some quantum mechanical weirdness continued on, but we're just going to briefly touch the subject and not get too in depth.